Welcome to the video on resonance structures practice. Before we start, I want to remind you that we can only move electrons in a resonance structure that are lone pair electrons or that are pi bond electrons. We can never touch a sigma bond when we're doing resonance structures. A summary of the 5 main patterns that we see in resonance structures. The allylic lone pair. So in this case, we're going to use 2 curved arrows to bring the 2 electrons off of the oxygen, the lone pair, down to form a double bond in between the oxygen and the carbon here. So the new double bond is going to go right here. And then in return, this double bond, this pi bond, these 2 electrons have to hop up onto the carbon. So if I draw the product of those 2 arrows, it will look like this. That's when you have an allylic lone pair. Remember, allylic means one away from a double bond. Second is allylic carbocation, and in this case we have 1 arrow that represents the electron movement. The 2 electrons that are in this pi bond move and form a new pi bond over here. And in return, the positive charge jumps over onto this carbon because now it is missing a bond. The third type is the lone pair adjacent to a carbocation. 1 arrow is going to be used in this one as well. When we have a carbocation that is next to an atom with a lone pair, we can take those 2 electrons in that lone pair, hop them down to form a pi bond. The product of that electron movement will look like this. There's always a conservation of formal charge if you haven't noticed already. This has a -1 here, a -1 here, a +1 here, a +1 here, a +1 here, a +1 here. So you're always going to have conservation of charge in all your resonance structures. The fourth way is when we have a pi bond that is in between an electronegative atom and a carbon. The 2 atoms have to have a different electronegativity. In this case, we have 1 arrow. What we do is we take that pi bond, so those 2 electrons in the pi bond, and they just jump up onto the atom that has a greater electronegativity. And so the result of this electron movement would be this species. Now, I told you had to have conservation of charge, and I hope you see here that there is conservation of charge. This top one is 0, and this bottom one is also 0. The negative and the positive cancel out. The 5th pattern that we see is when we have a benzene ring. So what happens is this pi bond that's in between this carbon and this carbon jumps over and becomes a pi bond in between this carbon and this carbon. And it goes all the way around the circle. This double bond jumps over here. This double bond jumps over here. This double bond jumps over here. And what we get when we're done is a benzene ring, now with the double bonds in a different spot. So that's a quick review of the 5 different patterns that we're going to see in resonance structures. Now for the first sample problem, I'd like to do this one. So what would be the appropriate final resonance structure that results from this sequence of arrow pushing? So this lone pair hops and forms a new pi bond here. This pi bond breaks and forms a new pi bond here, and then this pi bond breaks and forms a new pi bond here, and then this pi bond breaks and hops up onto the oxygen. So the way that I would think about this is I draw my normal molecule without anything moved yet. Okay, so I've drawn everything as single bonds. So I've drawn my framework here. And so now this lone pair forms a new pi bond here. So I'm going to draw that in. And then this pi bond breaks but forms a new pi bond here. So I'm going to draw that pi bond in. And then this pi bond breaks, so these 2 electrons form a double bond over here. So I'm going to draw that one in. And then these 2 electrons jump up onto the oxygen. And so I end up having now, instead of 4 electrons or 2 lone pairs up there, I have 3 lone pairs. Now I can't forget this double bond because that one did not get touched in this resonance structure. So this lone pair is gone and I have a new bond here. This pi bond is gone, but I have a new bond here. This pi bond is gone, but I have a new pi bond here. and then this pi bond has gone up onto the oxygen. Okay, so now let's look at formal charge. So in my original molecule, I had a formal charge of 0. And so in this final structure, my nitrogen has 4 bonds and 0 lone pairs. And so it has 4 electrons right around it. And in the periodic table, it is in group 5, but it has 4. So we take the group number minus the number of electrons and we get 1. So there's a positive charge on this nitrogen. Now I can kind of just see that the rest of these carbons all in the rest of the molecule here are all going to be just fine in terms of formal charge. But when I get to my oxygen here, I see that it has 7 electrons around it. It's in group 6. It has 7. So that's going to be a -1. And so this is going to be a negative charge. And so my overall formal charge is 0. And so that's good. And so that is my final structure. This was supposed to be an iClicker question, so let's do it now. Which of the following compounds does not have any reasonable resonance structures? How do I approach this problem? I jump immediately to D and I say, oh, this one's easy. This is the exact example that we just had on the pattern page. So that pi bond can move up and we can form this resonance structure, which is a valid resonance structure there. So D is not the answer. That one has a valid resonance structure. I jump right to E and I see that, oh, look, this is awesome. We can move these right around. And so that one has a valid resonance structure. That was exactly one of our patterns as well. Then if I look at letter C, this is exactly what we talked about, having a lone pair allylic to a double bond. So this lone pair can hop down, and then this double bond can hop up. And so this one has a valid resonance structure. And the same goes with B. I have a lone pair right next to a double bond. So this lone pair can kick down and we can kick that up on. And so these B, C, D, and E are exactly from those patterns that we just talked about a few seconds ago on a previous slide. However, if we get to letter A, this lone pair on the oxygen can't go anywhere because this carbon right here is sp3 hybridized. So we cannot touch any of the sigma bonds, so we cannot touch any of these. This cannot move down because this carbon can't have 5 bonds. Remember, in the line bond structure, it's assumed that there's a hydrogen there as well. And same with this double bond. There's no place for it to go. It cannot move into, because this is sp3. So A is your correct answer because there's no allylic lone pair. There's no allylic carbocation. There's not an electronegative atom double bonded to a carbon. And there's no benzene. And so A is the answer. A does not have any reasonable resonance structures. Now the next question, which of the following resonance structures contributes the most character to the structure of the overall resonance hybrid? We have a double bonded oxygen, and we have a nitrogen here that's got a negative charge, and then we have an sp2 hybridized carbon here. Okay, so if we move electrons around, we can see that in this case, letter D is all it did was it took the lone pair from the pi bond here and kicked it up and left that. And so that one's not a very good structure because nowhere in our instructions on patterns did we say, hey, let's just take a pi bond and split it and make a carbocation right next to a carbanion. We never said that that was feasible. And so D is not going to be a very major contributor. And if we look at E, we have that same situation. Now we can absolutely do this, but it's not a major contributor when we take that double bond and split it up the way we have in D and E here. So now let's look at A, B, and C. We know D and E are not major contributors. So as I'm looking at A, B, and C, trying to figure out which one is the best structure, I'm realizing there's a lone pair missing on the nitrogen. So let's add that in all cases here. Because in order for nitrogen to be negative, it's in row 5. It needs 6 around it. So it's missing a lone pair. Please note that on any exam question, it will have the right number of electrons to start. You won't have to do this step. Sorry about that. Okay, so now that we've added the lone pair in, on all structures, we can evaluate A, B, and C. If we look at A, we have a negative charge on the nitrogen and everything has an octet. If we look at letter B, we see that nitrogen does not have an octet, carbon does not have an octet, and oxygen is negative. So oxygen being negative is good, right? We want the most electronegative atom negative, but we got some octet things going on. So I think B is absolutely not correct. And then if we look at answer C, we have everything has an octet and oxygen has a negative charge. And so I think if we compared A and C, with nitrogen being negative in A and oxygen being negative in C, that the answer is in fact the letter C, where oxygen carries the negative charge and everything has an octet. So the answer there is C, the most stable contributor. So if we look at this example and try to figure out how we're going to practice maybe recognizing these patterns that we've learned, I can show you how I would think about this problem. And so remember, resonance structures are always going to use this double-headed arrow to indicate that we have resonance structures. And so I recognize this pattern up top first off right away. We have a lone pair right next to a carbocation. We can take that lone pair and we can kick it in to form a double bond. And so if I draw that resonance structure, it will look like this, with my new double bond right here. And then my positive charge is going to go on the nitrogen. So that's my first resonance structure. And I recognize that carbocation right next to a lone pair pretty easily. And so we went ahead and drew that structure. So if I look back at my starting molecule again, the second one that I recognize here is that I have this allylic carbanion. So I can take the 2 electrons in the lone pair, kick it into a double bond here, and then kick this up on to the carbon to make it a carbanion. And so if I draw that resonance structure, it's going to look like this. I hope it's not too confusing that I am fast forwarding the video through my actual drawing to save time to make the video a little shorter. Now notice I left what was indicated in the red electron pushing. I left that alone. I went back to my original. We're just looking at what happens with the blue arrow movement. And so we see that this is our resonance structure for just moving that allylic lone pair down and kicking the electrons back up onto the carbon. So that's my second resonance structure. And so then if I think about this third functionality here, this nitrogen with a double bond and the lone pair right on the double bond, we have not learned that that is a pattern that we could recognize moving. And so we're not even going to touch that. So that one doesn't even count. And so really we've focused on the carbocation next to the lone pair and the allylic anion. And so we've used those two. It turns out there is a fourth structure, and maybe you could have guessed by now. And that's the situation where we move both the red arrow electrons and the blue arrow electrons. And so we can imagine that fourth structure looks like this. And the way that I do this is I draw all of my single bonds, or the bonds that aren't being touched, out. So I draw all of those out, and I'm sorry this is looking very messy. So I draw all of my single bonds out. And then I go back and try to figure out where my electrons are, where my lone pairs are. So the red arrow indicates that there's now a new double bond here, and that we have the positive charge on the nitrogen. So I'm going to draw that and the positive charge here. And then the blue arrows, those 2 electrons hop down, and then that hops up. And so we have a double bond here, 2 lone pairs still on the oxygen, and then a carbanion on that carbon right there. And so now this would be my fourth structure. So I hope that helps you thinking about recognizing these patterns that we've used, right? So looking at this nitrogen here, we got nothing. So we don't have to worry about that. The other 2, we do have some movement that could happen. And so we can do one at a time to get the red, one at a time to get the blue, and then we do them both together to get the green. I know I went over this in class, but I'm just going to review real quick. Resonance structures in terms of which one is the highest contributor. There are 3 main rules. The first rule is that the most significant resonance structure has the greatest filled octets. So anytime we have a carbocation, that is going to be a minor contributor if compared to one that has carbon with an octet. Rule number 2 is that we want the fewest number of formal charges. And so in this situation right here, we have nitrogen. And so if we look at this example, we see the largest contributor is the one all the way to the left that has no formal charges at all on it. Once we draw that first resonance structure, we have a positive charge and a negative charge. So that is a major contributor actually, but it's not the largest contributor. And then if we look at the difference between the major contributor and the minor contributor, that carbon is not got an octet in the minor contributor. And so that's the big difference there. So zero formal charge all the way to the left is the largest contributor. Formal charges, but still octets, is the second. And then finally, the one without the octet. And the third rule is that we want the negative charge on the more electronegative atom. So the major contributor here, because the oxygen is negative versus this one where the carbon is negative. Now let's try these two structures. If I were you, I would pause this video as we do these two sample problems and just see if you can do these. Okay, so how I would solve these problems. First of all, I got to draw in my lone pairs. Okay, once I have my lone pairs in there, I know that I know what I can work with. Okay. So at this point, I see that I have a lone pair next to a carbocation, and I also have an allylic carbocation. So there's probably a couple different things I can do. So let's first of all take the lone pair, kick it in to form a double bond. And so let's see what that looks like. So my first resonance structure will look like this, with the positive charge now on the nitrogen. Sometimes you end up, in order to get all of the resonance structures, it's easy to go back to the starting one. So now if I draw electron movement, pretending the blue doesn't exist, right? So draw electron movement where my pi bond electrons hop in to fill that empty p orbital on the carbocation, we end up with this structure where we have a carbocation out here and the double bond is moved. And so now this is an example where we had really two different patterns that we recognized and both pushed towards the same empty p orbital. And so you kind of had to do them one at a time. Notice that all three have a positive charge, and so we have conservation of charge, and so that's a good thing. And I think we're good. So these are the three structures for that compound. And now if we look at the second example, I see a lone pair, a negative charge next to a pi bond. And so I'm going to take this lone pair, kick it in to form a double bond here. And in response to that, this double bond has to hop up onto my carbon. If I draw that, there's now a double bond here with a nitrogen, a lone pair, and a hydrogen. And so that's my first structure. And if I now take this lone pair and push it down to form a new bond here and kick this up on, so my second structure looks like this, shown in blue. And if I now take this lone pair and kick it up to form a pi bond here and kick this up onto the carbon. Okay, so that's my fourth structure. And then if I do this one more time, the lone pair kicks in to form a double bond, and then this pi bond breaks and kicks up. My final structure looks like this. And so I have 5 total structures, but I'd like to show you something really neat. It turns out that if I had gone back up to this compound, look at my red arrows, and I had moved these all over one, like a typical benzene ring would be, we'd get this resonance structure right here. So we get this resonance structure either by going all the way around the ring or just by moving them around the ring. So we can either have the negative charge move around the ring to get there, or we can just move the bonds inside the benzene ring around. So there's how you solve that one. There's 5 total structures. So the next problem I want to talk about is which of the following options contributes the most character to the overall resonance hybrid? And this is the molecule that we are given. So there we go. We have that compound. Now, which one is the major contributor? In this case, we have nitrogen with a positive charge and carbon with a negative charge. Everything has an octet. In this situation, we have nitrogen with a positive charge and oxygen with a negative charge, but it looks like everything has an octet. With this situation right here, we have a negative charge randomly out here on this carbon, which in the original was an sp3 hybridized carbon, which we cannot touch. So this is absolutely not even going to happen. And letter D has a carbocation and a negative charge on our oxygen. So this one right here does not have a filled octet. So that one also does not work. So we have to decide which is better, having a negative charge on the carbon or having a negative charge on the oxygen. And I hope that by now you're going to say, oh yeah, negative charge on the oxygen is much better. And so the answer here is B. Okay, awesome. I hope that helps you when you're thinking about resonance structures. I think the bottom line is that we have to think about those patterns that we learned and see if we can find those patterns, recognize them, and then go ahead and push the electrons. Awesome. Good luck.